All right. So we're now back into what is the meat of what we're going to be talking about today, matter of units of measurement. Our topics in particular, classifying matter, measurements. What do we mean by precision and accuracy? Significant figures, oh, there they are again. Scientific notation, oh, there it is again. And dimensional analysis. This is going to provide us with the basic mathematical stuff that we need to be able to understand and talk about to make sure that we're talking the same language when we talk about the math setups. Okay, so here's our basic understanding of matter and what it is and some of the words that we use for that. Here's how we make those measurements. What do we mean by precision and accuracy? How do those numbers apply into what we're doing? And then how do we use them to actually do stuff for chemistry? So that's where we're going. Okay, questions, comments, problems at that point? I hope not, but let's go. So matter. We'll talk about classifications of matter. Now I'll show you the physical states on the next slide, so we'll come back to that. We're going to talk about purity on 5 and 6. Is it pure? Is it impure? And what do we mean? How do we quantitate that? What are we looking at? We'll talk about physical properties. Now, or properties, one of them being physical. Physical properties are things that can be observed with no changes to the material. So I can look at it and I can say, ooh, that's gold. I can look at it and say, that's a cube that has a particular size. That's a physical property. I can measure sizes, I can measure volumes. Those are physical properties. We can talk about its chemical properties. But in order for us to talk about its chemical properties, the actual chemical properties, we're going to have to break down those materials. That's necessary to understand what is this material. So if I wanted to identify a particular substance that I'd been given, we'd have to do some chemical analysis where we broke that down into its individual components, meaning the individual elements that are in it, probably in what ratios, so we know exactly which material we're talking about. And we can talk about some other things, but in order to do those kinds of measurements, I have to break it. I can't leave it in one piece and make those kinds of measurements. So we have to destroy those. Chemical properties cannot be done without destroying that structure. Okay. We can also talk about intensive and extensive properties. Now, an intensive property is not dependent on the amount of the material. Things that would fall into the intensive category: temperature, melting point, density. Doesn't matter what size of material I have, those are all going to come out the same. Okay, now I understand that when we talk about temperature, it may be a different temperature at the top than it is at the bottom if we're talking about a very large sample. That's not what I'm talking about. Okay, we're not talking about those kinds of things. That's a different level of complexity than beyond what we're talking about. Okay, when we talk about extensive properties, those are dependent on how much of that material I have. So we often don't just talk about gold. We talk about how much gold do I have? Well, I have a mass, I have a volume, I have a specific amount of that gold that we're dealing with. For chemistry, that's very important. And so how we measure that in terms of the mass, looking at a balance, how accurate is that balance? I'll get back to the accurate and precise in just a minute. What is the volume? How much of that material do I have in the liquid form? Okay, so we can talk about the mass in the solid form and liquid in the and the volume of the liquid. Okay, but that brings us to our physical states. So now let's talk about those physical states. Hopefully we're pretty familiar with some of the physical states. We have solids, liquids, and gases. If you want to think about something we're all pretty in common with, we can talk about water. Water is one of my favorite things to talk about. It has lots of very interesting properties that we will get to, which make our world work the way it does. Without water being what it is, we would have no world. And that's really important. I think it's important. I wouldn't live without it. We have solid, which for us, we typically talk about as ice. We have our liquid, which is the actual water. We talk about it as water. And then we have our gas, which we talk about as steam. Okay, those are our common names for those phases. We can talk about the phase changes that happen between these. I'm not overly worried about the phase changes right now. We will come back to that at the end of this term. Okay, but those are the ways that we can talk about how we go between solid and liquid. That has one term, it's melting. And we go from liquid to solid, that's freezing. So there is some directionality that we associate with the word. Okay. What we're more interested in is what that thing looks like. Now, in the solid state and what properties it has. So in the solid state, things are very, very closely compact. Now, how compact they are on a microscopic level depends on what it is. But they're very, very compact, and they're held in a very fixed pattern. So it's very difficult for us to make changes to that. Now, some things can make changes. You may know soft metals. They can change their shapes. That's true, but it doesn't change the structure in the solid. We've just changed the shape, which is actually an extensive property, not an intensive one. The intensive property, the actual atomic and molecular structure within it has not changed. Okay, as long as it's solid, that's the way it is. Now, there are some technicalities to that if you know about them, let's talk about them here. Okay. When we talk about our liquids, we've moved into a phase where there's much more space between those things than there was before. So now we have these individual atoms. We're talking about atoms in this particular element at this point. That's what I'm talking about. And we'll define those terms a little bit later. I'm just, for anybody who knows what they are, that's what I'm talking about. And we have those individual parts, these little balls, that are now able to move against each other. So they have the freedom of movement. Okay, there is some space in between them, and they're free to move. One of the things that we talk about when we talk about water is that it is very capable, and always does, assume the shape of whatever is holding it. Okay, so it will assume the shape and the size. Okay, so again, the way that that physically looks, that will change, but it doesn't change what's in it. All right, so we haven't changed any of the chemical properties of that. We've only changed the physical, how it's arranged. All right, and when we add some more energy to it, we can get it into the gas phase. So you're probably familiar with this. You do this on the stove, right? So you add heat to it. It gets it into the gas phase. We've added energy by doing that. And now these things are moving all over the place. And they're not easily contained. Okay, gas gets everywhere unless you put a container around it. Right? It will occupy any space it has available. Doesn't matter what that space is. Okay, all of the molecules are as separated, the atoms are as separated as they can be. So if I were to attempt to break them down any further, I would have to break apart that atom. Okay? And so that's what we're talking about. When we talk about these physical states, we're talking about how closely packed they are, how much space is in between them, and what are the physical properties that we're looking at. Okay, so that's the kind of thing that we're talking about. All right, so hopefully there are no questions about that. Let's talk a little bit more about some of the terms that you've probably heard me throwing around. Elements, compounds, and mixtures. You've probably heard these terms before. So I want some definitions for those terms. I like definitions. A substance is a form of matter that has constant composition and distinct properties. Now, a substance could be anything. Right? It could be an element, it could be a compound, it could be any number of things, as long as it has constant composition and distinct properties. Okay? So we can talk about, salt water. That's a substance because it has constant composition and distinct properties. Okay? Elements. We can talk about elements. Elements are the things we find on our periodic table. So if I were to pull over my exam handouts, this guy is my periodic table, and all of these little designations that are on here, those are my elements. We will get to what they are and why they're like that and all the rest of that later on. But that's what I mean by an element. What I mean by an element is that I cannot break that down any further. So I have individual atoms. We'll talk about what atoms are a little bit later, actually in the next lecture. And we can't break it down any further unless we start breaking apart those atoms. When we talk about compounds, they can't be further separated by physical means. So my elements, things like that, I can talk about pure silver, I can talk about hydrogen gas, I can talk about oxygen gas, things like that. all right? And those are the things that can't be broken down any further except by chemical means, right? They're the ways that they exist in nature, yada, yada, yada. And we'll talk about why some things have two and some things don't later. A compound, on the other hand, can be further broken down, but it can't be further separated by physical means, okay? So one of the things that we talk about here, your most common experience with this, is water. Water is composed of two elements, hydrogen and oxygen, in a fixed ratio, 2 hydrogens for 1 oxygen. Okay, that's what that H2 and the O mean. I can't break that down any further than that, just physically. I can't heat it up and it'll bust apart. I can't freeze it and it'll break apart. If it breaks apart, it's still molecules of H2O. Okay, so my physical means cannot get that any further separated. We would have to separate it by chemical means if we wanted to break it down anymore. I also have mixtures. Now, mixtures can be combinations of any of these things. All right, could be combinations of an element with a compound. Could be an element with or two compounds. Could be two elements. Any number of these things can be a mixture. All right, it's a combination of two or more substances which can be separated by physical means. All right. Typically, we talk about things like that. And actually, I mentioned salt water before, and I was mistaken when I said it, so sorry. But there are ways that we can break that down. So they can be separated by physical means, that mixture. So I can get the salt out of the water. This is something you've probably seen. If you take some salt water and you let it stand for long enough, then the water goes away, it evaporates, and you're left with the salt. Okay, so that's a physical means. So it evaporated, and that's a physical change. Right, so that's a mixture. I like to talk about mixtures in terms of things like ice cream. Oh, I love my ice cream. We can talk about things like Rocky Road. Most of us are familiar with Rocky Road. It's an ice cream that has different parts. It doesn't matter where I look at it, it doesn't look exactly the same as everywhere else. So that's a mixture. But then again, we have other mixtures that are things like salt water, where I can't necessarily tell what the difference is. All right. They are things that are very difficult for me to see what's what. Okay. I might give you a picture like this and ask you to define for me, is it an element? Is it a compound? Is it a mixture? What is it? And I always am going to follow that with, how do you know? So I want you to think about that for a minute. I want you to pause here and think for a minute about what you see in all of these. All right. So based on the definitions that we had before, I'm going to come back and look at my definitions again because I like them. So my A is just single balls that are in there by themselves. I would define that as an element because it's just one thing. Okay. Now, when I look at this one, I might initially look at this and say, well, it could be an element, it could be a compound, because it could be two things, that are held together. But what I notice when I'm looking at this is that they're all the same color. And if they're all the same color, that means that they're the same thing. Now, why one is this way and one is this way, that we'll talk about later. But this is still an element. So this could be something like silver, where it exists by itself. This could be an element of H2 or O2, where they're bound together. And I can't break those two H's apart without doing something chemical. All right. Now, if I look at this one right here, I notice that I have one thing in the middle with three things attached to it that are all the same. So I've got two different things that are bound, and they're bound in a fixed ratio. So if I look at my definitions, it's not an element. It's not something that has the same thing all the way throughout it. It has two different things. They can't be separated by physical means. So that's a compound. Right? So this guy right here is a compound. There are any number of things that would have this kind of structure. I could have an N in the middle and three H's, which is ammonia. Okay, that's the common name for that stuff. And that would fit into a compound structure. H2O would also be a compound. So they're fixed ratio of things that are bound to each other. And what I mean by fixed ratio is that if I talk about something like H2O, that is a compound. H2O2 is also a compound. And those two different things have different compositions. Okay, so the amount of those things related to each other is important. We'll get back to that. Don't worry about it. When I look at this guy down here at the bottom, I now know that I have some elements and a compound that are mixed together. Okay, fine. That has to be a mixture. And it is a mixture. Okay, so that's the logic in determining what each of those things is. Now, one of the things that I was going to talk about, and I apparently don't have a slide about it anymore. Let me go back, sorry. I talked a little bit about Rocky Road and how it's not consistent across, right? So inconsistent versus consistent. I think that I actually defined this in a later lecture, but I'm going to go ahead and talk about it here because I mentioned it. If it's not the same throughout, and so it depends on where I sample it from, that we determine its structure. That's inconsistency we call heterogeneous. Hetero, meaning different, genius. I don't actually know what that word means, but it means that there are different parts within it. I mean, that's the colloquial definition. I should have looked up what genius actually meant. Consistent, on the other hand, is going to have that same root word, genius, but it's going to be homogeneous because they're all the same. Okay? Different, same. All right. So if you can tell where you are, no matter where you are, it looks the same, then that's homogeneous. If, however, you can physically look at it at any level, be it macroscopic or microscopic, and see that there are differences in it, then that's heterogeneous. Okay? So those are our classifications of matter. Do we have any questions at this point in time? All right, I'm going to stop this sharing. I'm going to stop this recording. And I will see you back in a little bit. Thanks, guys.